Welcome back, everyone. We've gone deep on a lot of different topics here, but today we're revisiting something that, well, it really kind of blew people's minds last time we talked about it.
Mhm.
This crazy connection between two blocks colliding and
Yeah.
pi.
Yeah, that's right. We're jumping back into this thing called the pi collision problem. It was made famous, at least as far as I know, by that 3 blue, 1 brown video. So you got this little block just sitting there minding its own business. Then along comes this bigger block moving towards it on this perfectly smooth surface, no friction, nothing. And they hit, obviously. The small one bounces off, hits a wall, and here's the wild part. How many times everything bounces around, including those wall hits? Well, if you do this just right, it starts to look like the digits of pi.
Yeah. And you know that original video? It just went totally viral, didn't it? Like,
Yeah.
everybody was talking about it. But there's actually even more to uncover here. We're talking about links to, get this, quantum computing, like straight up Grover's algorithm. And you know what else is crazy? It turns out that nobody's ever actually completely 100% proven how these collisions line up with pi forever. So this time, we're not messing around. We're going deep on why this whole thing works the way it does.
Totally agree. It's way more complicated than you might think at first. Just to remind everyone about the basic setup, imagine the blocks are the same size, same weight. You'll get 3 collisions total. Make that big block 100 times heavier. Suddenly you're at 31 collisions. 10,000 times heavier. Something like 314 collisions. A million times heavier. About 3,141 collisions. Those numbers, they look awfully familiar, don't they?
Seriously, it's wild.
It is.
And just to be clear, in the real world, things are messy. We're talking about a super idealized situation here. Like, imagine a surface so smooth, there's literally zero friction, and the blocks hit each other perfectly. No energy lost at all. So no cool thwack sound in our little physics experiment, haha.
Yeah.
And if we really wanted to get crazy with a supermassive block, well, then even Einstein and relativity would have something to say about it. But let's not go there today. We're sticking with nice, clean, classical physics.
Right. Because even without all that extra stuff, the main thing that blows my mind is how those collisions line up with pi. Like, you just make the big block heavier by these nice, even factors of 100, and bam, you see pi's digits.
Exactly.
Yeah.
It's just elegant somehow.
Now, we're going to keep you waiting a little bit for the quantum computing part. All that stuff about Grover's algorithm. We're going to have a whole deep dive just for that with a real expert theoretical physicist, Adam Brown. But think of this deep dive as like the second edition of how to solve this classic problem. We want to make sure everyone really gets why pi shows up here. And then that sets us up perfectly to talk about the quantum stuff later. Plus, we want to dive into some of the weird details that most people skip, like how this whole thing isn't even 100% proven mathematically.
All right, so we're setting the stage for some big reveals later on. But for now, let's get back to basics. I mean, this problem, at first glance, it looks super simple, right? Just two blocks bumping around. So how do we even start to untack something like this? Where do we go from just blocks hitting each other?
Well, the best way to attack any problem, especially one that seems, overwhelming at first, is to just lay out what you know. Like, what are the basic rules of physics that are definitely at play here?
Okay, so for these blocks, what are those big important rules that we got to keep in mind?
Well, the two big ones, the real heavy hitters, they're conservation of energy and conservation of momentum. So with energy, we're talking specifically about kinetic energy, the energy of motion. The formula for that is 1/2 times the mass multiplied by the velocity square. Looks like this. Half mv's, though. So we've got our big block, mass m1, moving at velocity v1. Small block is m2, moving at v2. Add up their kinetic energies, that's half m1 v1 mil m1, plus m2 v21. That's the total kinetic energy in our system. And now, conservation of energy, this total amount, it has to stay the same throughout the whole collision process. That's the rule. We're assuming, like we said, no energy gets lost anywhere.
Right, okay, I'm following. And then there's momentum, right?
Right. Momentum is even simpler, thankfully. It's just mass times velocity mv. So total momentum of our two blocks, m1 v1 plus m2 v2. Conservation of momentum. This total value, it also has to stay the same, but here's the catch. It only stays the same when the blocks hit each other. When that small block slams into the wall, well, it's transferring momentum to the wall, so the total momentum of our system changes a bit there. But between the blocks themselves, momentum stays constant.
Okay, so we've got our physics cheat sheet laid out.
Mm-hmm.
Conservation of energy, conservation of momentum. Now what? We just stare at these equations and hope for inspiration.
Well, sometimes a good picture is worth 1,000 equations. It might seem kind of basic, but visualizing things can really help. In this case, what's changing all the time? The velocities. V1 and V2, they keep bouncing around with every hit. So what if we made a graph? Horizontal axis is v1, vertical axis is v2. Now, as our blocks collide, their velocities change, right? So the state of the system, what's v1, what's v2 right now, that traces the path on our graph, we call this state space.
So instead of trying to keep track of two separate numbers going back and forth, we're basically watching a single dot move around on this map, this state space.
Exactly. And this whole idea, the state space where you take like all the important information about a system and turn it into a point on a graph, well, it's a super useful tool in physics. Plus, you know what's cool? It actually connects to that quantum computing stuff we'll talk about later.
Oh, interesting. A little foreshadowing there. Okay, so we got our point moving around in V1, V2 state space. But what about our energy equation? That whole EV-Vux stuff, how's that look on our graph?
That energy equation, a half 1 villa 1 v1 blood plus half m2 v2 half per equals some constant number. Well, if you plot that out, it makes an ellipse. The exact shape of the ellipse depends on the masses of the blocks. The size of it, that depends on how much energy we start with, which really just means how fast that big block is going initially. But here's something really cool. It turns out that the initial speed of the big block, it doesn't change how many total collisions we get. It just changes how fast everything happens. The main thing is, as those velocities change, our little point on the graph, it has to stay on that ellipse. If it moves off, well, that means energy isn't conserved and we've broken physics.
Right. So it's all about that elliptical path. But, I remember in the original video, they talked about wanting to use a circle instead of an ellipse, something about pi and circles, right?
Absolutely. Pi. Circles, they just go together. And circles, they're all about symmetry, right? Ellipses, they're kind of like stretched out circles, not quite as symmetrical. Now, one of the best tricks in problem solving is to look for symmetries. And since pi is showing up, well, maybe thinking about circles is the way to go.
Okay, but how do you actually turn that ellipse into a circle? Sounds like math magic to me.
It's kind of like a clever trick, yeah. We basically just change how we're looking at our graph. Instead of plotting v1 directly, let's plot something else. Call it x, and it's going to be the square root of m1 times v1. Looks like this. m1, v1. Same thing for v2. We'll plot y equals v2. Now, if you take these new guys, x and y, and plug them into our energy equation, after a bit of algebra, you get something beautiful. X plus y equals some new constant. And that, my friend, is the equation for a circle.
Whoa, neat. So just by changing our perspective, by looking at these new adjusted velocities, we turn that ellipse into a perfect circle. And our little point, our system, it's got to stay on that circular path now.
Exactly. We've basically created this new system where energy is still conserved, but now it's all about moving on a circle. Okay, so let's think about where we start on this circle. At the very beginning, the big block is moving towards the little one, right? So V1 is negative. Little block is at rest, so V2 is 0. Translate that to our x and y. Well, it means we're starting at the leftmost point of the circle. Y is 0. X is some negative number.
Makes sense. So blocks collide, boom. What happens to our point on this circular map?
When those blocks hit our point, it jumps to a new spot on the circle. It can't leave the circle because that would mean energy isn't conserved anymore. But where does it jump to? Well, here's where momentum comes in.
Right, momentum. But we changed our coordinates, right?
Yeah.
Does that mess up our momentum equation?
Good point. But you know what? In our new x and y world, that momentum equation, remember, m1v1 plus m2v2 equals a constant. It becomes m1x plus m2y, a new constant. Look familiar.
Wait a second. That's a straight line.
Bingo. It's a straight line on our xy map. So right after that collision, our new x and y values, they got to be on the circle and on that line. Now, a line and a circle, they can cross at like 2 spots at most. One of those spots is where we were before the collision. So the other spot, that's got to be where we end up after the collision.
Okay, so that collision in the real world, it just looks like a hop from one point to another on our circle map. And that line, that momentum line, tells us exactly where to hop.
You got it. Now, there's something really important about the slope of that line. If you do a bit more algebra, you'll see that the slope is negative square root of m1 over meter to meter raised to a meter. This slope, it all comes down to the ratio of the masses. And that's going to be super important for figuring out why we see pi here.
Right, that mass ratio keeps popping up. Okay, but what about the wall? Remember that little block? It bounces off the wall too. What's happening on our map when that happens?
When that little block hits the wall, it bounces back, right? So V2, its velocity flips direction. Now, on our graph, y is just m2 times v2. So flipping v2 just means flipping the sign of yx, the big block's velocity, it doesn't change at all because it's not involved in the wall downs. So picture this. Our point is at xy, then bam, wall hit. Now it's at xy. just a straight jump up. And since momentum changed because of the wall, well, the line we're using on the graph, that momentum line, it changes too. It's got to go through this new point.
Right, so we're hopping around on this circle, following these momentum lines, then doing these vertical jumps when we hit the wall. When does all this bouncing around finally stop?
It all ends when both blocks are moving to the right. That means both V1 and V2 are positive. In our X and Y world, that's the top right part of the graph where X and Y are both positive. But there's one more thing. The little block has to be going slower than the big block. V2 less than V1. On our graph, that means being below a line with a slope of M2 middle 1. So we've got the special zone on our map. Top right part, below that line, that's the end zone. Once we get there, game over. No more collisions.
So what started as this physics problem with blocks, it's now like a geometry puzzle. We start on the left side of the circle, move down and to the right along a line, then jump straight up, then down and to the right again, and so on, until we reach that end zone. And each of those down and to the right lines, that's a collision.
Exactly. We've turned physics into geometry. And now pi being involved makes a lot more sense because we're literally dealing with the circle.
And you said earlier that a steeper slope for those lines means more collisions? Makes sense, right? Steeper means you're going down faster, so it takes more zigzags to get to that top right corner. But how does the slope connect to that mass ratio we keep talking about?
Remember, the slope is conum on 1 molar 2. So if the big block is way heavier, M1 is much bigger than molar 2, that slope gets really big, really steep. Like if the mass ratio is 100.1, the slope is mana 1001, which is mana to 10. Pretty steep. And in that case, yeah, we get 31 collisions, 31 of those zigzag lines on the circle.
Okay, starting to see the picture here. But how does pi itself, the number, how does it come out of this whole zigzagging on a circle thing?
Take a look at those points where our momentum lines hit the circle. See those arcs connecting them? They all look kind of the same size, right? Well, it turns out they are the same size. And there's a really cool geometry theorem that proves it. The inscribed angle theorem.
Inscribed angle theorem. Care to refresh my memory on that one?
Sure. Imagine you've got a circle and you pick 3 points on it. Let's call them P1, P2, and P3. Now draw lines from P2 to P1 and P2 to P3. That makes an angle at P2, right? The theorem says this angle is exactly half the size of the angle you'd get if you drew lines from the center of the circle to P1 and P3.
Interesting. Okay, but how does that relate to our zigzagging lines and those arcs on the circle?
So take 2 of those down and to the right lines, the ones that represent collisions. They make an angle, right? We called it theta, and it's determined by the slope. And since the slope is always the same, all those theta angles are the same. Now, using that inscribed angle theorem, we can show that the arc between those 2 lines, it makes a central angle of 2 times theta.
So each time we go down and right, then up, that's like taking a step at 2 times theta along the circle.
You got it. And we keep taking those 2 theta steps until we hit the end zone. Basically, how many times can we fit 2 theta into the whole circle? The whole circle is 2 pi radians, right?
Right. So the number of collisions, it's got to be something like 2 pi divided by 2 theta, which is the pi divided by theta.
Exactly. Now, imagine for a second that theta was like a really nice number, like 0.01 radians. Then pi divided by 0.01 would be 340.159, and so on. And hey, look at that. The first 3 digits are 314.
That's where the digits of pi are coming from. If that theta angle was just a simple power of 10, then yeah, dividing pi by it would give us those pi digits.
Right. But remember how we said things get a bit more complicated? That theta angle, it's not actually a nice, simple power of 10 that matches the mass ratio perfectly.
Right, because the slope is connected to the square root of the mass ratio, and theta, and something about an arctangent or something.
You're on the right track. Remember, the slope of those lines is lion 1 mortal white 2. Now, the tangent of that angle theta, it's like the inverse of the slope. Specifically, tan theta equals a mon 0.1. So for a mass ratio of 100.1, tan theta is 0.1. But that means theta itself, it's the arctangent of 0.1. Not just 0.1, but arctangent is 0.1.
Ah, okay, so theta, it's not a simple decimal. It's this whole other function, arctangent of the square root of the mass ratio flipped around.
You got it. It's a bit more involved, yeah. But now, here's where a super handy tool comes in. Physicists and engineers love this one. The small angle approximation. Basically, if an angle is really small, like really tiny, the tangent of that angle is super close to the angle itself. Think of it like this. Draw a circle. If you make a tiny angle, the length of the arc it makes and the length of the tangent line at that point, they're almost the same.
So for those huge mass ratios where that square root stuff gets really tiny, the arctangent of that tiny number is basically the same as the timing number itself.
Exactly. And that's the magic. The reason those collisions line up with pi so well is because we can use this approximation. Because arc 10 pi and arc is super close to 0.1, arc 10 I were 1,000, 1,000, 1,000, we're 6 and 1,000, 0 and 1,000 are 0, 0, super close to 0.01, so on.
Okay, so this small angle approximation, it's like the bridge between that complicated arctangent stuff and those nice powers of 10. And that's how we get pi to show up so clearly. But wait, didn't you say this whole thing wasn't completely proven? Like, there's still some mystery here.
Yeah. There is. The small angle approximation, it's awesome. It works super well, but it's still an approximation. There's a tiny bit of error there. And here's the thing. Imagine if pi, like way down in its decimal expansion, had a ton of nines in a row, then a number flipped over. Like, imagine it was 3.14159999999 forever, then suddenly changed. If that happened, then our way of counting collisions using that approximation, it might be off by just one collision for a super, super huge mass ratio.
And proving that pi doesn't have those crazy long strings of noise, that's a super hard problem.
Yeah, it's one of those problems mathematicians haven't cracked yet. So we see this beautiful connection. The collisions look just like pi's digits. It works amazing in practice. But proving it 100% for any mass ratio you can think of, that's still a mystery.
Wow, so even though we understand how it works, there's still this little piece missing. It's like we almost have the whole puzzle, but not quite.
That's the beauty of math, right? There's always more to explore. But even though that full proof is still out there, we can still write down an exact formula for the number of collisions. It just uses all the precise geometry we talked about, no approximations. Oh, and another thing, that base 100 mass ratio. It's not like special or anything. If we were using binary numbers, then using powers of 4 for the mass ratio would show us pi's digits in binary.
This whole thing is just so mind-blowing. But, some people might say, why bother? It's just blocks hitting each other and it's all idealized anyway. Does this even matter in the real world?
It totally matters. First of all, this idea of starting with a simplified version, making things perfect, it's like the foundation of how we solve problems in science. You strip away all the messiness, the friction, the little bits of energy loss, and then you see the core idea, the fundamental relationship. Then, once you understand that, you can add the messiness back in. Like, imagine we wanted to include energy loss in our collision problem. We could just make the circle shrink a little bit with each collision. That would represent the energy going away.
Makes sense. Start with the clean version, then add the real-world details back in later.
Exactly. And second, by going for this perfect, idealized situation, we often find connections between things we never expected. Remember how we mentioned that original paper? They compared these colliding blocks to, get this, a beam of light bouncing between mirrors. Who would have thought? And then the biggest connection of all, this whole math structure we've been talking about, it shows up again in quantum computing, specifically in Grover's algorithm, which is a super important part of that whole field. It's crazy how these seemingly totally different things are actually connected deep down.
Which is exactly what we're going to be diving into next time. So excited for that.
Right. But the main point here is when scientists and mathematicians simplify things, it's not just to make their lives easier. It's about finding the deep connections, the hidden patterns that we might miss otherwise. It's in those pure idealized situations that we often make the most progress and get those aha moments.
Wow, this has been one heck of a journey. We started with blocks bumping around and ended up with geometry on a circle, hidden connections to light and mirrors, and even hints of quantum computing. And the craziest part is the full 100% proof that this all ties back to pi. It's still out there, waiting to be discovered.
I know. It just shows you how even something that seems simple can have so much depth to it. Take a moment. Picture that circle, those zigzag lines. It's amazing how physics and geometry are so intertwined.
And don't forget to join us next time when we dive into the quantum world. We're talking about Grover's algorithm and seeing just how deep this rabbit hole goes.
Oh, and before we go, one last thought for you to chew on. We saw how the energy of those blocks, that basic physics law, it turned into a circle in our state space. But what about other laws of physics, other systems out there? Could those map onto different shapes, maybe even weirder ones? And if they do, what kind of crazy connections might we find? What else is hiding out there in the universe, just waiting for us to connect the dots?
That's a great question. I guess we'll have to keep exploring to find out.